in this lesson, we discuss the divergence test and the integral test. Each of these tests and the tests that are to come in later lessons are all used to determine whether a series converges or diverges. So let's start here with the divergence test. It's one of the more simple tests that we'll use. All right, so here I go. So here's what the divergence test says. Okay, if the infinite series, so this is our notation for an infinite series, okay? If the infinite series converges, then the limit of the series as k goes to infinity must be equal to 0. Okay, this statement here is the contrapositive of this statement. Remember, the contrapositive of a statement, let me, like off to the side here, if P then Q, that's a conditional statement, right? If P then Q. The contrapositive would be not Q implies not P. This here would be the contrapositive of this statement. And what we know is true from logic is if a conditional statement is true, its contrapositive is also true. If a conditional statement is true, then its contrapositive is not true. So this here is the contrapositive of the original statement. So we can understand the divergence test as follows. If the limit of a series as k goes to infinity is not 0, if you're able to prove that the limit of a series is not 0, then the series does not converge. That is to say, the series diverges. So this here is really going to be the way we prove, the way we show that a series diverges. What you and I will do over and over again in order to show that a series diverges is you and I will prove, well, the limit of the series as k goes to infinity is not 0. And that's enough to prove that it diverges. So let's look at some examples. Okay, everybody, here's our first example. There'll be 3 different examples that I walk us through, 3 or 4 of them. We have the infinite series k over k plus 1 as k goes from 0 to infinity. We want to know, does this series diverge or do we not know? Okay, is it inconclusive? So this is just an example of us using the divergence test. Okay, so what we need to do, let me move the screen up a little bit. All right, that's enough. All right, so if I consider the limit of k over k plus 1 as k goes to infinity, like that. Can you and I show that this limit is not 0? Because if we are successful at showing that this limit is not 0, then that's enough to prove that this series diverges. So let's consider it now. You can, first of all, please notice that this series here, this expression as k goes to infinity, the numerator is tending to infinity and the denominator is also tending to infinity. So because this is the indeterminate form that we have, we can use L'Hopital's rule to evaluate this limit. So I'm using L'Hopital's rule, okay, everybody? That means I'm going to consider the limit as k goes to infinity, and I'm going to differentiate the numerator and differentiate the denominator. The limit becomes the limit of 1 over 1, right? The derivative of k is just 1. The derivative of k is 1. The derivative of 1 is 0. So this is really 1 over 1. So then this limit is equal to 1, which is not 0, obviously. So because the limit is not equal to 0, we know the series diverges. That's the conclusion. All right, so that one was pretty simple. Let's look at a new example, all right? So look at here. We have now a brand new series, and it is 1 plus 3 to the power of k all over 2 to the power of k as k goes from 1 to infinity. Again, this is an infinite series, and you and I want to practice using the divergence test. So therefore, let's consider what is the limit of 1 plus 3 to the power of k over 2 to the power of k as k tends to infinity. All right? So I think what we can do here is split up the fraction. In other words, we can say, well, this is equal to the limit as k goes to infinity of 1 over 2 to the power of k plus 3 to the k over 2 to the power of k. And we can say, well, this is equal to the limit as k goes to infinity of 1 over 2. I can say this is to the power of k. I can write it that way. Plus the limit as k goes to infinity of 3 over 2 to the power of k. Like that. All right, cool. Now, please notice that as 1, one's fixed. The numerator is fixed at 1 while the denominator continues to grow. So therefore, this entire ratio here, this is approaching 0 as k goes to infinity. While this one here, as k goes to infinity, 3 halves raised to the power of k, this is approaching infinity. So basically what we have, let me move this up a little bit. So basically what we have is 0 plus infinity. So it's infinity, which is not equal to 0. Therefore, the series diverges by the divergence test. All right, excellent. Let's look at another example. So this is our next one. Okay. So far it's been pretty smooth sailing, trying to prove that an infinite series diverges. All right, here we go. Now, remember what the divergence test says. And let's also be careful about what it does not say, all right? The divergence test says that if we can prove that the limit is not 0, the limit of the terms of the series is not 0, then we can conclude that the series diverges. The first statement of the divergence test says if the series converges, then the limit is equal to 0. What the series does not say is it does not say that if the limit is 0, then it converges. That's not what it says. It says that if it converges, then the limit is 0. Here, you know what? I think it's worth going all the way back here. Bear with me. Here it is, right here. If the series converges, then the limit is 0. This does not mean that if the limit is 0, then it converges. Okay, that's not necessarily true. Okay, in other words, as far as logic is concerned, if P implies Q, that does not imply that Q implies P. That is a false conclusion. This is not, I should say, this is not necessarily true. Just because P implies Q does not necessarily mean Q implies P. All right? So just because we're able to show that the limit is 0 does not necessarily mean the series converges. Maybe it does, maybe it doesn't. We're not sure. The only thing we can conclude is if the limit is not 0, then we can conclude the series diverges. So once more, I just want to really drive this point home here. Just because the limit is equal to 0, the limit of the terms of the series, as k goes to infinity, just because we can show that it's equal to 0 does not necessarily mean the series converges. I think that's important for this example that we're looking at the moment. If I can get back there. Is this it? Yes, this is it. We're going to see here that the limit of the terms of the series is actually approaching 0, but that does not necessarily mean it converges, all right? So let's get into it now. The limit of 1 over k as k goes to infinity. Now, the numerator is actually fixed at 1 while the denominator continues to grow. So then this is equal to 0. But just because the limit is 0 does not necessarily mean the series converges. So we say this test, the divergence test, in this case is inconclusive. That's our final answer, is that the divergence test is inconclusive. Maybe this series converges, maybe it diverges. We're not sure. Now, I will tell you that soon we will show that this series is actually a very important series. It's called later on we'll get into it, it's called the harmonic series, and it actually diverges. But we're not able to prove that using the divergence test. So the divergence test does not help us with this series. Okay? We're going to have to prove that it actually diverges using another strategy, using a different test. Okay? So here the answer is inconclusive. We're not sure. Okay, so I hope that was clear. All right, let's jump into, I think I have just one last example for us. I have this infinite series, k starts at 1, of 1 over k squared. Now, here, once again, it's pretty much the same thing, isn't it? The limit of 1 over k squared as k goes to infinity. Once again, the numerator is fixed at 1 while the denominator continues to grow. So then this limit is equal to 0. Again, by the divergence test, we have the final answer of inconclusive. We're not sure whether this series converges or whether it diverges. We just say it is inconclusive by the divergence test. Now, later on, we will actually say that this series converges. It actually, the answer is it converges, but this example here is all about us using the divergence test. That's what we're practicing right now, okay? And so if you use the divergence test, basically the divergence test doesn't help you. The divergence test doesn't help you make any kind of conclusion here. You would have to use another test to show that this actually converges, okay? It's actually a p-series, so you should remember from earlier studies that this is a p-series, and because p is greater than 1, we know it actually converges, okay? But that's using a different test. If we stick to the divergence test, inconclusive. Okay, I actually want to get into a very, very, very important series called the harmonic series. Okay, the harmonic series is defined to be 1 over k as k goes from 1 to infinity. Written out as a series, it would be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 and so forth. This harmonic series, this series is very, very important, and we know that this actually diverges even though the terms of the series approach 0. So in other words, even though the limit of 1 over k as k tends to infinity, even though this limit is 0, this series diverges. If you actually look at what this tends to, so if you start looking at the sequence of the partial sums, you'll see that it's not approaching any one real number. So we actually can use an integral actually to prove that this series actually diverges. Actually, this leads us to the next test, which is called the integral test. The integral test. Let's look at it now, okay? Okay, here's the integral test. So suppose we have a function that is continuous, positive, and decreasing. Okay, so these are the conditions of the test. Okay, the function is continuous, positive, and decreasing for x values that are greater than or equal to 1. And let the terms of the sequence be able to be written as a function f of k for k equal to 1, 2, 3, etc. Okay? Then here comes what the test says. The infinite series and the integral of your function from 1 to infinity, they either both converge or they both diverge. Either they both converge or they both diverge. Okay? In the case of convergence, and this is very important, the value of the integral does not necessarily equal the value of the series. So if you find that the integral converges, let's say it converges to the number 1, let's just say, that means the series converges. But it does not necessarily mean that it converges to that same value as the integral is, that the integral does, okay? But if the integral converges, the series converges. If the integral diverges, the series diverges. Okay, so let's look at some examples. Okay, so our first example here is the infinite series of k over k squared plus 1 as k goes from 1 to infinity. Now, for a second, I know this is asking for the integral test, but I do want to have you at least think about the divergence test. If you use the divergence test would lead you to the fact that the limit of the terms of this series actually approaches 0. And so the divergence test would be inconclusive. So the divergence test doesn't help you here. So what do you do when the divergence test doesn't help? You can try using the integral test. Okay, so let's try it now. So here is the integral test. So it is going to be the integral from 1 to infinity of x over x squared plus 1 dx. Now, we know that this is a rational function and we know it is continuous. Nothing, no value, no real value for x causes this rational function that defines the integrand to be undefined, okay? Because x squared can never be negative 1. So this denominator can never be 0. So this will never be undefined. So it is continuous and it is positive at all times because your values go from 1 to infinity. They only run through positive values. So then this is a positive value. This is positive because it's being squared. So anyway, this is positive. And then this is decreasing because the power in the denominator is greater. And so this, the larger the values of x become, this denominator is growing a lot faster than this numerator. I mean, it's being squared. So this is definitely a decreasing function. So all the conditions are met here. All right, so here comes the question. Can you and I evaluate this integral? Now, if this integral, if it converges, then the answer is the series converges. If this integral diverges, then the answer is that the series diverges. All right, so let's get into it now. So how are we gonna do this? Well, from earlier studies that there's more than one way you can evaluate an integral. Maybe you want to consider a trig substitution. Maybe you want to consider partial fractions. Maybe you want to consider making a u substitution. So if I make a u substitution, I would say let u equal x squared plus 1. That would mean du is equal to 2x dx, which means that 1/2 du is equal to x dx. So then this integral then can be rewritten. And in this case, when x is 1, u is 2, and this is still going to be infinity. And then this would be of the form, let's see, 1/2 du over u. Okay, so then this is 1/2 the integral from 2 to infinity of just 1 over u, like that, right? Which, of course, you can write as 1 over u and then du, okay? So here we know that this leads us to 1/2 times the absolute value, times the natural log of the absolute value of u from 2 to infinity. Let me see if I can scroll down here. Okay. All right, very good. You know what? Wait, I moved too fast here. I'm sorry. Let me go back because you should notice, as I just realized here, that this is actually an improper integral. So I need a limit. So let me go back here if you don't mind. I'm erasing. Let me go back. Okay, cool. So I don't have to go back that far. Anyway, so this is equal to 1/2 times the limit as b goes to infinity of the integral from 2 to b of 1 over u du. I'll write it that way. Anyway, so then this is equal to 1/2 times the limit as b goes to infinity of the natural log of the absolute value of u evaluated from 2 to b. But when I reverse the substitution, let me go back here. When I reverse the substitution, or I guess I don't have to, I don't have to reverse the substitution because I changed my limits. That's right. So then this is equal to 1/2 times the natural log of, let's say, b, right, minus the natural log of 2, like this. Very good. I forgot my, I got to go back. I forgot my limit notation. I got rid of my limit notation too soon. So 1/2 times the limit, we'll be able to evaluate the limit in this next step. The limit of the natural log of b minus the natural log of 2, like that. All right, cool. So then this is equal to 1/2, and as b, I don't need absolute value bars around b or around 2 because these are positive values. Anyway, as b goes to infinity, this is approaching infinity. So this is infinity here, and then this is minus a natural log of 2, like that. So this entire thing is just infinity. So we just found that the integral diverges because this is not a real number. Therefore, the series also diverges. Cool. I hope that was clear. Let's move on now to the next example. So the next example is the infinite series of 1 over the square root of 2k minus 5 as k goes from 3 to infinity. Okay. All right. So let's go now. Let's consider the integral. This is the integral test. Oh, by the way, same as before, if you use the divergence test will not help you conclude anything. It will be inconclusive because as k goes to infinity, the terms of the series will approach 0 because the numerator is fixed while the denominator continues to increase. And so therefore this ratio is actually approaching 0. So the divergence test will be inconclusive. So we're grateful that we have the integral test at our disposal here. Okay, so we have the integral from 3 to infinity of 1 over the square root of 2x minus 5 dx. This is the integral test. Now, let's not forget, like I forgot in the previous example, right, that this is a improper integral. So let me use a limit here. I'm going to say the limit as b goes to infinity of the integral from 3 to b of 1 over the square root of 2x minus 5. I had forgotten that in the previous example and had to go back, right? All right, so let's actually evaluate this integral. So what you can do here is use, you can use a u substitution if you'd like. So you can say let u equal 2x minus 5. That would mean du is equal to 2 dx. That means half of du is equal to dx. So then this is equal to the limit as b goes to infinity. And it is infinity here. But if you plug 3 in for u, for x, you get 2 times 3, which is 6, 6 minus 5, which is 1. So it's now 1 to infinity. And then this becomes 1 half du over u. So then this is equal to 1 half times the limit as b goes to infinity of the natural log of the absolute value of u from 1 to infinity. Let me see if I can scroll. There we go. So let's keep going. So then this is equal to 1 half times the limit as b goes to infinity. I'll actually evaluate the limit in just a second. Of the natural log. Oh, oops. Hold on, folks. I'm sure some of you caught it. Where is it? Right here. This right here, upper limit is b. Sorry about that. Go back. I'm probably just going too fast here, which means this is b. All right, cool. Let me go back. Make sure you change that in your notes if you didn't catch it already. Okay, so now when I'm here, I knew I made a mistake because I was like, I can't plug in infinity here. Natural log of b minus the natural log of 1. And as b tends to infinity, the natural log of b is approaching infinity. And then this natural log of 1 is 0. And so this is equal to infinity. So because the integral diverges, the series also diverges. Cool. I'm glad you are tracking with me. I have one last example for you, at least one like this, okay? All right, so we have the series of 1 over k squared plus 4. Oh, I like this example. As k goes from 0 to infinity. All right, so let's consider the integral from 0 to infinity of 1 over x squared plus 4 dx. Remember, we need a function that's continuous. This rational function is continuous, right? The only values of x that would make this rational function not continuous is any real number that would cause the denominator to be 0. And the only way the denominator is 0 is if x squared is negative 4, which is the opposite of 4. But x squared can never be can never be negative 4 because any real number squared is positive. So this rational function is continuous. It is positive because this term is positive, and so is this one. It's all underneath a positive number. This whole thing is positive. And it needs to be decreasing, and it is. The numerator is fixed, and the denominator continues to grow and grow and grow. And so the values of this series is actually decreasing. So all the conditions are met. So please don't take those 3 conditions for granted. Okay, so let's do this. You should realize that this is the value of this integral here. Well, first, let's write down that it is an improper integral. I tend to rush sometimes and not write down the limit, so let's make sure I don't skip that. So it's the limit as b goes to infinity of 0 to b of 1 over x squared plus 4. And what I was anxious to say earlier is that the answer to this integral here is inverse tangent. I hope you are really familiar with that by now. So this is going to be the limit as b goes to infinity of 1/2 times inverse tangent of x over 2, like that. And this is evaluated from 0 to b, okay? And this is just from our knowledge, our prior knowledge for integrating this type of expression. When you have 1 over the sum of 2 perfect squares here, then this is like the little formula, if you will. We talked about this in earlier studies. All right, so let's actually continue simplifying here. So then this is the limit as b goes to infinity. I don't want to evaluate that just yet. Of, of 1/2 times inverse tangent of b over 2 minus inverse tangent of 0 over 2. Let me put some parentheses there. I actually can factor out that 1/2. I'm going to do that now. So I have 1/2 out front. And I will simultaneously evaluate the limit. Now, as b goes to infinity, you have infinity over 2, so this becomes infinity. And the angle whose tangent value is approaching infinity is pi over 2. Let's not forget what the tangent function looks like. So if I can draw this really quick, I'm going to sketch the graph of tangent. I could also use the graph of inverse tangent. So this is the graph of tangent. Let's not forget that tangent is undefined at pi over 2 and negative pi over 2, any odd multiple of pi over 2. So you should see that as your angle gets infinitely close to pi over 2 on the left, then the function values are approaching infinity. And that's exactly what this is approaching. As b goes to infinity, this is approaching infinity. So the angle whose tangent value is approaching in positive infinity is pi over 2. So the answer here is pi over 2. Now here, 0 over 2 is 0. An inverse tangent of 0 is 0. 0 is the angle whose tangent value is 0. So let me actually, I'm not going to erase my tangent graph just in case you're still looking at it. So let me just continue writing down here. So then this is 1/2 times pi over 2 minus 0. So it's half of pi over 2. So pi over 4, I almost stopped right there in pi. So pi over 4 is the value, watch this, pi over 4 is the value that the integral converges to. But be careful. We are going to say that because the integral converges, the series also converges, but the series does not converge to pi over 4. But it does converge, okay? All right, so there's our final conclusion there. All right? Awesome. Now, before we end this lesson, I want to very briefly go through the p-series, okay? If you have a p-series, and now we've studied p-series in earlier studies, but if you have a p-series, we know that it converges if p is strictly greater than 1, and it diverges if p is less than or equal to 1. So let's look at some examples really quick like. All right, so we have the first one here, and we are asked to determine whether or not this series converges or diverges. Let's keep in mind that this series can be rewritten as 1 over k cubed. Now, we know that this is a p-series with p equal to 3. Therefore, we know that this series actually converges. That's done. All right, let's look at another one. Okay, so this one will be the infinite series as k goes from 1 to infinity of 1 over the 4th root of k cubed. Now, keep in mind that this can be rewritten as 1 over k to the power of 3/4. Now, this is a p-series, and p is equal to 3/4, which is less than 1. Therefore, the series diverges. All right, and that one's done as well. All right, cool. Let's look at one more, and then we can kind of turn this lesson in, okay, as complete. All right, last one. We have the series, as k goes from 4 to infinity, of 1 over k minus 1 quantity squared. Now, this might be, now not clear on whether this is a p-series or not. So let us write out this is what I recommend. I want us to write out a few terms of the series so that we can clearly see what we're dealing with here. Okay, so if k is 4, then we have 1 over 3 squared plus. Now when k is 5, we have 1 over 4 squared. When k is 6, then we have 1 over 5 squared plus, etc. I trust that we can see the pattern. So with that being said, can't we then rewrite this series as a p-series? Isn't this series then the same thing as 1 over k squared? Isn't 1 over k minus 1 squared, as k starts at 4, which gives us these terms, wouldn't it be the same thing then as 1 over k squared, but we'll just let this time k start with 3, because 1 over 3 squared, 1 plus 1 over 4 squared, and so forth. So this series here, which the way that this was written here, it's not a p-series, right? The way it's written. But if we write it this way, then it is a p-series. So what I would love to encourage you to do is sometimes it's beneficial to write out a few terms of the series so that you can see, oh, this series actually can be written this way. And when it's written this way, it's clear, it's more evident, oh, this is actually a p-series and my p-value is 2. So our final conclusion is that this series actually converges. All right. What I would like to point out to you is, if I can give you, I don't mean to make you dizzy here, but can you look at what this test says? You have to have a series starting from 1 to infinity. So hold on just a second. K has to start with 1. But down here, if I can go back, k doesn't start with 1. K starts with 4. Isn't that a problem? Or actually, k starts with 3. But k is supposed to start with 1. So we're actually missing the first two terms, right? K equal to 1 and k equal to 2. Well, even though we're missing, if you will, the first two terms, when k equals 1 and when k equals to 2, adding or removing, in this case, those two terms have been removed. Adding or removing a finite number of terms actually does not affect the convergence of a series. All right? If this series, this is what we're saying, if this series converges when k equals 3 to infinity, well then 1 over k squared will also converge when k starts with 1 to infinity. All right? So that's a really important fact that we want to be careful about. Okay?